and welcome to the Microsoft Academic Research Exchange. I'm Marcy Collinson, Director of Worldwide Academic Research at Microsoft. During this session, Flying into the Future, How to Assess the Environmental Impacts from Aircraft Emissions, we'll examine aviation's environmental challenges, highlighting advanced modeling, air quality, climate effects, and mitigation strategies. Dr. Ling Lim of Manchester Metropolitan University will present recent research on fleet analysis and discuss computational and methodological issues, plus future directions. If you have questions during the presentation, please submit them using the Teams chat at any time during the talk to engage with Dr. Lim. Dr. Lim, welcome, and thank you for being here today.
Hello, everyone. I'm Ling Lim from Manchester Metropolitan University. I'm a research fellow here, and currently I'm working on research projects looking into how aircraft emissions are affecting us in terms of air quality and climate. So let's get started. Today, I'll tell you a little bit about aviation climate effects and how we model them. But before we do this, we need to know, why should we care? Why do we need to care about aviation impacts? We need to then know, what are the climate effects and why do we need to model this? And how do we actually model this, and what are the challenges, and how do we overcome these challenges? Where are we heading into the future? So first of all, why should we care? Well, the main thing is aviation is the fastest growing transport sector. As you can see from the figure, even with all the disruption that we've had in the past, for example, 9/11, SARS, COVID, it always catches up. So aviation continues to grow. It might dip a little, but it carries on growing. And even though it is only 2 to 3% of global carbon emissions, it is rising, and it is rising rapidly. And from the figure, you can see that even though it is a small fraction from the total global CO2, but the fraction is increasing. The gap between the blue line, which is the total, and the black line is closing in. And then aviation is really hard to decarbonize. There's physics challenge, there's engineering challenge, and unlike surface transport, for example, which is easy to change from, for example, petrol to electricity, for airplanes is really, really hard because you need to essentially redesign the aircraft. And even with a redesign, you need to be able to carry all the batteries that you need, and it needs to go the distance. And a lot of planes, the majority of it is going long haul. So, for example, electricity is just not an option at the moment. And planes or aircraft emissions affect not only local air quality, but it also affects the climate. So aircraft has a tougher engineering and physics problem than cars and power plants. And it's growing, and that's why we need to care about it. So what are the climate effects? We know that it's a combustion process, so it will have CO2, but it also changes atmospheric composition. So in this case, for example, it's the nitrogen oxides, NOx, and water vapor. And it also changes the cloudiness. So cloudiness in this case the changes is coming from the soot particles and the sulfate particles from the fuel. And this is changing how the cloud is being formed, is changing the thickness of the cloud. And most importantly, or unique to aviation, it also has contrail cirrus. So contrails are the little wispy white clouds that you see coming out from the plane. And when this contrail persists, it can spread and it becomes contrail cirrus. And all these effects depend on location, not only just where in terms of longitude and latitude, but also in terms of altitude. And it depends on the meteorology as well. So when it comes to all these effects, we've got the warming effects, which are the CO2, the net NOx or nitrogen oxides, the water vapor, and the contrast cirrus. And then we've got a very small cooling effect from aerosol. And what we don't know at the moment is the impact of these aerosols on cloud formation. And at the moment, we are not sure whether it's warming or it's cooling. Why is modeling needed? We have measurement techniques available, but measurements is a backward-looking technique. Models tell us the future, and it can also tell us what will happen under different situations. So what are the challenges in measurement? Here is an example from the EU project Aviator. We have an aircraft, and at the back of the aircraft, there is a probe, which is circled here. And the probe essentially has to be weighed down by concrete blocks, because as we change the thrust setting of the aircraft, you can imagine is a huge force, and we need to make sure that the probe is actually measuring the emissions instead of being blown away by the aircraft. What else can models do? Models can also provide information on past situations, current situation, and also give us an opportunity to see what the future situation may look like. In this example, there is 4 different scenarios of the future. So this is all in 2050, and we've got different world as such. We've got a world where we've got high technology uptake. We've got a world where there's low demand. We've got a world where there's less international travel. So with modeling, we can do all these future world scenarios. In addition, we can also have a look at different policy and mitigation options. So this figure shows, for example, what are the contributions from technology? What are the contributions from improved operational air traffic management? We can see what are the contributions from sustainable aviation fuel, and we can see it at different time slices, different future time slices. So that's these are some of the reasons why modeling is needed. So one thing to reiterate is that it's not measurements versus models, but it's measurements plus models. We can't have the models without measurements, because measurements are used to provide input into the model, and also as a validation point to make sure that the models are doing what they're supposed to do. So how do we model these effects? So we need to somehow turn the flights into physics. So what we do is first we get a flight database, and here is an example of different flight routes for a specific year in time. Then we put the flight data into an emissions model. This is where we change the flight data and we compute the fuel burn, we compute all the different emissions, like how much particles is being released, how much NOx is being released. And then we take these emissions and we put it into a chemical transport model. So a chemical transport model will say, if you have 1 kilogram of NOx or nitrogen oxides being released in the tropics, what will happen to the ozone? And how does it changes with the wind? How does it changes with different meteorological condition, different time of the day? And finally, we then put the results of these concentrations of, for example, ozone into a climate effects model. We will find out what is the balance, the heat balance in the atmosphere, or what we call radiative forcing. So basically, from this very simple system, you can see that there's a lot of data and a lot of computing. In this next few slides, I will focus on the emissions model and the chemical transport model. So how do we turn flights into emissions? So first we need some input data, and at the very basic level, we need to know the aircraft performance. So this is how much fuel is being consumed by the aircraft for every second it is operating. We also need to know the engine emissions index. So for example, for NOx or nitrogen oxides, how many kilogram of NOx is being released for every kilogram of fuel that is being burned. And finally, we need obviously the flight information. So we need to know the routes, including the profile. Profile means at what flight altitude is it flying. We need the aircraft type, and we need the frequency. So how many aircraft is being flown on a specific route at a specific time. So the modeling process is then we take the flights, we compute the fuel burn, and from the fuel burn, we compute the emissions on a 3D grid. Remember that aviation not only have a longitude and latitude, but it also has an altitude as well. So this is illustrated in this figure. So we have, imagine this is the Earth, and we have an aircraft flying. So it departs from an airport, and then it arrives at another airport, and it has a path. The path is not only traversing horizontally, but it's also traversing at an altitude. Then for each of these aircraft, we need to know what type it is. For example, is it an A320 or is it an B777? And what type of engine is it? Then from the aircraft type, we'll get the fuel flows, and from the engine, we'll get the emission index or the EIs. And finally, putting all this together, we need to know how many flights there are at every the point at which we want to model. And from all this, we get fuel burned, we get distance travel, and we get the emissions. So as you can see, there's a lot of data, and at Manchester Met, all this data is stored in a database, and our model essentially run from this database, which is the MS SQL server. So it's very database driven, and depending on the application, we will make some simplification. For example, if we know that a specific aircraft is flying a specific route that is within a distance band, we then say we only model it once and assume that the same distance band is used. This will basically save computation time. And the results is then we have a map of where the fuel is being consumed, not just on a longitude, latitude basis, but also on an altitude basis. And this is some of the output from our model. So a single flight, as you can see, is easy and quick. But when you have 40 million flights per year, it is not easy. And 40 million flights per year is what we are currently, that is present day situation. So in the future, you can imagine if we were to look at 2050 or 2070, we're looking at a lot of flights in a year. How do we then turn emissions into concentrations? Again, we need some input data. So what we need is we need emissions, aircraft, obviously, but we also need non-aircraft and natural sources. So I will explain why later in the modeling process. We also obviously need meteorology because we need to know how much sunlight is there. We need to know what is the water situation is. We need to know how the winds are blowing. And finally, we also need some initial and boundary conditions. What does this mean? It means we want to make sure that when we do the simulation, we don't always start from zero. We need to always start from what are the concentration level at the start of the simulation? What is the temperature at the start of the situation? How does the meteorology looks like at the start of the simulation? So that we don't have what we call a cold start event. So in terms of basic modeling process, we have, first of all, we have a spin up. Spin up means once we have all these initial and boundary conditions, we run the model, but we're not actually using the results. We're just getting the model to a stage where we can actually look at the results, because we don't want a cold start situation, like I mentioned before. We need to get it in a chemical transport model. We need to get it to a steady state situation. And then when we run the simulation, we essentially need to do, for every simulation, we need to do it twice with two different input data sets, with and without aircraft sources. And this is where the non-aircraft and not natural sources come into play, because aircraft emissions is so small compared to other sources like land sources or power generation or even natural sources, that if we just run everything, we're not going to be able to see the aviation signal. So what we do is we run it once with aircraft sources, and then we run it once without, and then we essentially take the difference just to make sure that we get enough signal. There's no noise in it. And also because the atmosphere is non-linear, we need to make sure that whatever signal we're seeing is not just a linear relationship. And how do we do the simulation? We use an on-premise high-performance computer at the moment. So, and how long do we run it for? It depends on the perturbation. So, for example, for ozone, you don't need to simulate for, say, 20 or 30 years. Whereas for some perturbations, you will need to run it out for a long time before you get to a situation where the results can be used. So this is an example of 1 month run for ozone. So you can see the spatial patterns. It depends on where the emissions being released. It depends on the meteorological condition at a specific time. And basically the gist of it is that without high performance computing, the simulation simply isn't possible. It would take really long to run because it's very complex. So what are the challenges in modeling the climate effects from aviation? So from the modeling process itself, we've got input uncertainties, just like any modeling exercise, garbage in, garbage out. There's also scientific understanding. So there's a lot of things that we don't know at the moment, especially on the cloud physics side of things. And with modeling, we will need to make assumptions and simplifications. So depending on the application, some of the simplifications is acceptable, but sometimes it's not. In terms of data, so data availability can be a challenge as well. So for example, flight data, we have obviously now we've got flight radar, for example, but it doesn't cover the smaller aircraft. And there are some places where we don't have information, or it's really hard to get information, some countries. And because aviation is such, especially for global climate effect, we wanted to have a global emission data set. And also we have very large data set. This is not just on the flight data. We've also got meteorology, and we've got the input, we've got the output. And what else in terms of data? In terms of data, we also have differences in format. So depending on the sources, for example, if you have flight data from flight radar is different from flight data from another source. We've got different resolutions, so the emissions data set are usually not the same resolution as the meteorology data set, and they're also not in the same coordinate systems. So these are just some of the examples. Then in terms of computation, obviously we've got model complexities. So over the years, models have improved, and with more scientific understanding, model becomes more and more complex. You've got the 3D grid resolution. You don't have only longitude, latitude, but also altitude. And then you've got the simulation time steps. So do we want to model every single minute, every single day, every single week? And the time steps depend on what we're trying to look at, what perturbations are we looking at. And then we also have input and output data size that we need to, the input data needs to be read in by the model, and then it will produce an output data that is most of the time, it could be in the terabytes. So we've got all these challenges. So basically what we need is, as scientific improvements come into play, we also need better computational improvements, as in the hardware that we use to run these models. So where are we heading? So in terms of the science, we are knowing more. There's a lot more research, and this research will lead into better models. And with better models, we can then include more decision support tools. For example, we can have mitigation options built into the models to test on the go, as we say. In terms of the computational resources, we've got obviously AI and machine learning, but with this, there's also challenges, because especially in the climate front, because our climate is changing, AI or machine learning can only learn from the past. We don't know what's going to happen with the future. So we will need to see where this leads us. And obviously now cloud computing. So one of the things that Manchester Met has been looking at is to moving our database into Microsoft Azure. And also we are moving our HPC into the cloud with the Microsoft Cloud HPC system. And all this is currently being tested. And again, will this mean that we may have lower costs because we don't have on-premise hardware, we don't need to maintain it. But again, we don't know because we're still in the testing phase. So basically, sustainable aviation cannot just come from aircraft and engines, but it also needs to have better computing facilities, or else we wouldn't be able to know if any of these changes are actually better for the environment. There you go. That's a quick tour on how we use modeling to assess the climate impacts from aviation. Thank you very much for watching.
Thank you, Dr. Lim, and thank you for attending this session of the Microsoft Academic Research Exchange.